Good morning, afternoon, and evening, and welcome to the Transdermal Model Seminar presented by Dr. Jessica Spires and Bill Van Osdol. A few housekeeping notes. For optimal video and audio connection, we highly recommend you close out any additional web or streaming applications that may affect your internet bandwidth. We take your privacy rights seriously. By attending this call or participating in the Q&A session, you are allowing us to contact you for follow-up. This call is being recorded for future playback. Today's course structure will have lecture and examples followed by a lively Q&A session. Please use your questions panel to submit your inquiries at any time. We know there are lots of ways to spend your time, and we appreciate you spending the next 60 minutes with us. Now, before we begin, we have a quick poll question. How would you classify your experience with GastroPlus? We'll give you a few moments to select your answer. Are you a beginner, intermediate, and advanced user? Or maybe you've never used the software before and today's your first introduction. Just a few more seconds here. Great, so we've got some intermediate users and beginners. You guys are in the right place. Now it's my pleasure to introduce today's moderator, Mr. Dan O'Connor, Director of Business Development for Simulation Sciences. Take it away, Dan.
Thank you very much, Arlene, and welcome all to our second attempt at the Transdermal Dosage Routes seminar. So again, thank you for rejoining us this week to overcome some of the difficulties that were in place with GoToMeeting last week. Wanted to just give you another opportunity to join us for live webinar series, actually, which have been underway this week. This is with our sister company, Monolix, Lixoft, who has the Monolix suite. And tomorrow and Friday, they'll be continuing their live webinar series on QSP. So you can find a registration site on our website at simulationsplus.com. Additionally, for those of you that have time later this year in July, we have 3 additional seminars scheduled, subjects to be determined, but they will be on additional products that we have, DDD Plus, Membrane Plus, and PK Plus. So if you're interested in any of these, dissolution, membrane, or PK analysis, please join us on those dates for those series. And again, there'll be more information that'll be coming shortly, either on our website, LinkedIn, or other. I thought I'd start just with a brief exercise in why I think dermal is very important. On the left-hand side of the screen is a 30-foot tree in my backyard. Now, while this tree looks to be vital, alive, and well, it's actually dead. On the tree, is in the close-up, is leaves of 3 flea. This is poison ivy, which I live in Connecticut. I like to say is the state flower, tree, plant. It's everywhere. And it's on our dogs, which have then transferred poison ivy to me. So I've been very focused in on skin over the last couple of weeks. And I've received from a variety of sources, friends, colleagues, etc., various remedies that included ocean water. And I want to thank my colleague, who will remain nameless, from St. Louis, who said, Dan, why don't you try the last suggestion and just jump into the ocean? The good news is, later in July, I will do just that. Hopefully, my rash will have been transitory at that point, and I'll be over it. But skin is an amazing organ. It's the largest organ in the body. And today we have 2 scientists who will be taking us through a bit of an exercise on what we can do with GastroPlus to better understand what the skin offers as a route of administration for drug. First, we'll be talking about Dr. Bill Van Osdol. He's a principal scientist. He studied at the University of Virginia and holds a PhD in biophysics. In addition to his vast knowledge and work on in silico modeling. He's worked specifically on extending the development of multi-compartment models for topical and percutaneous drug delivery in GastroPlus. Jessica Spires, who's a senior scientist, will be our principal presenter today. She's been with us for almost 8 years as a PhD in biomedical engineering from Case Western Reserve University. Jessica is also a senior scientist here at Simulations Plus and has served as a principal investigator in a collaboration with the FDA over the last couple of years to specifically extend dermal physiological based pharmacokinetics models developed for topical dosage forms and transdermal delivery systems. So both our speaker and our supporting scientist are experts in the study of transdermal dosage routes. So without further ado, let me introduce Dr. Spires. Jessica.
Thank you very much for the introduction, Dan. Let's see. Okay, hopefully you all are able, to see my screen. Okay. So I'll go ahead and get right into it. I want to thank you all for coming despite the issues with the timing. So now finally for on June 10th, we can start to talk about kind of the dermal delivery and how you would model this in GastroPlus. Just as a reminder, these were kind of all of the additional dosage routes that we have in GastroPlus. So you can have the ocular route of administration, the pulmonary route, specifically the oral cavity model, also intramuscular and subcutaneous injections. And of course, what we'll be talking about today is going to be this dermal or TCAT model. Okay, whether you're looking at topical administration or transdermal administration, this would kind of be the additional dosage route that you would be using for that. So, so our TCAT module was originally developed in collaboration with GSK. I believe we released it in 2014. And so the first thing that we did when we were developing this was, we had to take the very complex organ of the skin, which has a lot of different parts to it. So you've got the epidermis at the top here. Top layers of this, of course, are going to be the stratum corneum, which are several layers of kind of dead or very inert cells. Beneath the epidermis, you're going to have the dermis layer. That's going to be the vascularized part of the skin. Okay, and then beneath the dermis, you're going to have subcutaneous tissue. So it's kind of, question of whether this really counts as part of the skin or not, but it's going to be there, and it's possible for drug to diffuse down through there. In addition to these major parts of the skin, though, there are also a lot of different aspects to the skin. So you're going to have hair follicles. So you're going to have your hair shaft here. You're going to have the bulb of the hair, and then you're going to have waxy sebum layer that's surrounding the hairs. You're going to have sweat glands that are in the skin. You're going to have nervous cells. Okay, so there's a lot of different things going on in the skin that we kind of had to boil down to have a more simplified mathematical model that can still describe what's going on. Okay. The diagram that you see down here is kind of the representation of the TCAT module that we have in GastroPlus. Okay, so on the top layer, you're going to have a vehicle here. Okay, if you're doing topical dosing. You can also do it the other way around, where you're dosing systemically, and then you can turn on the TCAT module. So you can have drug going from the systemic circulation into skin. Okay. But usually what people are looking to is the cases where you're dosing topically. So you'll have some topical vehicle here. Okay. The skin itself is going to be divided into kind of 3 bulk layers. Okay. Epidermis is going to be divided into stratum corneum, which is going to be the major barrier part of the skin, and then the viable epidermis, which is going to have the living cells beneath it. Okay. Beneath the viable epidermis is going to be the dermis, and again, these are going to be living cells. And only once you get down to the dermis is there the possibility for transport to systemic circulation. Okay. And then beneath the dermis, you're also going to have the subcutaneous tissue, which is also going to be a vascularized tissue. In addition to these bulk layers, as you can see, we also include the hair follicle unit. Okay, so in particular, you're going to have the possibility to have the sebum route here, and which can be very significant for certain drugs. Okay, so you can have compound going down from the vehicle into the sebum, and then from the sebum into the viable epidermis and dermis as a sort of alternate route. And then, of course, you're also going to have the hair itself, and we divide that into a hair lipid layer, sort of a lipid layer surrounding, and that's going to be surrounding the hair core. For the diagram over here, this is just a quick look at all of the major processes that we have included in the TCAT module. Okay. So within the vehicle, you may have a single homogeneous phase, or you could have emulsions. And in the case of emulsions, you would have a continuous phase and dispersed phase droplets. Okay. If you do have a dispersed phase, you can have release from those droplets. Okay. Whether you have a single phase or two phases, you can have dissolution and precipitation occurring. You can have evaporation of the vehicle, and you can also potentially simultaneously have evaporation of the API itself. And then, of course, you'll have absorption into the skin. Okay. Once you're in the skin layers, there's the possibility for binding in all of the skin layers. Okay. Once you get down to the viable epidermis and dermis, there's also the possibility for metabolism. And again, once you reach the dermis, then there's the possibility to have systemic uptake. Okay. So this is just kind of a simple slide showing all of the major processes that we include in the TCAT module. And of course, I'll go into some more detail about all of these. One important thing to remember also when you're modeling skin is that there are regional differences in the skin in different parts of the body. Okay, so one of the things that we did when we were developing this module was we not only just had to think about skin generically, but also what's the location of the skin. The thickness of the skin layers can vary in different locations, okay? And also the perfusion, the blood flow can be different. And in particular, it's generally going to be high, about an order of magnitude higher in the head than it is in the other parts of the body, okay? So, when you're doing your own modeling or looking at data, this is something that you need to think about is where exactly was this topical vehicle applied, because that's going to have some implications for delivery and absorption. As you may be aware, GastroPlus has some pretty extensive modeling, pediatric modeling. One good thing is that at birth, the skin is going to be pretty much fully developed. Okay, but as you can see, as you look at kind of the prenatal fetal embryonic skin, then you're going to see less and less differentiation. So, if you're modeling the skin of the very premature infants, then those are the cases where you may really need to look into the modeling, and make sure that that's going to be valid. Okay. There are going to be some differences in the skin thickness with age, and this is just showing some of the data that we've collected about this. But really, there aren't going to be any huge differences between, again, from going from full-term infant to children to adults. Okay, but if you are doing the pediatric modeling, and especially once you get down to the babies, this would be something that you'd want to think about. Okay. So this is just kind of showing the TCAT module and also showing where you can select this dosing region. Okay, so when you look at this drop-down menu, you'll usually see the default physiologies have two parts. The first part is going to be the species, and the second part is going to be the region. Okay, so for the human physiology, we're going to have arm, leg, abdomen, back, face, and scalp as the defaults. Okay, and we're also going to have kind of a special case of having an in vitro sample from abdominal skin. Okay. As you can see, we also include the physiological parameters for several preclinical species. In the case of the mini pig, we were able to differentiate according to region. But for the rat and the mouse, we weren't able to get such specific information. So in these cases, we just kind of have a general, whole body average. Okay. As with other parts of GastroPlus, we also do give you the ability to create custom physiologies. So, if you do need to model a species that isn't included here or a region that isn't included here, then you can find the specific parameters, physiological parameters, and create a custom physiology. This would also be the case where you have some kind of special condition or disease state type skin. Okay. The major things that you would want to think about if you do need to create a custom physiology would be the thicknesses of the different layers and the hair follicle density, and also the blood flow in the dermis. Those are going to be the major things. Okay. So what are the different types of formulations? So this is showing, I think this was from guidance or some type of release from the FDA, classifying different types of dermal vehicles. Okay. So for the liquid formulations, as you can see, it's going to be pretty straightforward. If it's clear and homogeneous, you have a solution. If it's a solid dispersed in a liquid, it's going to be a suspension. And if it's an emulsion, then it's classified as a lotion. Okay. For the semi-solid formulations, as you can see, it's going to be a little bit more complicated, but ultimately it's going to kind of boil down to one of these four things. You know, it'll be a gel or a cream or an ointment or a paste according to the properties of the semi-solid formulation. Okay. So how does this relate to the transdermal or topical dosage forms in GastroPlus? So if you look at the drop-down list, all of the ones that start with TD, these are going to be the transdermal ones that are going to be used with the TCAT module. Okay. And as you can see with this little asterisk at the bottom, all of these transdermal dosage forms are going to require 4 basic inputs. Okay. You need to know the dose. You need to know the dose volume. You need to know the application surface area on the skin, and you need to know the application time on the skin. Okay. And if you're modeling a liquid solution, these are the only 4 things that you need. Okay. If you're modeling a suspension or an ointment or a paste, then these are going to be suspension dosage forms. So in these cases, you would also want to know some type of information about the particle size distribution. You know, what's the mean particle size? You know, what's the range of it, or so on. Okay. If you're modeling a lotion or a gel or a cream, these are going to be the emulsion dosage forms. So again, in these cases, you might have, for example, if you have oil droplets in water, the water would be your continuous phase and the oil droplets would be your dispersed phase. So in these cases, you would also need to have some information about your dispersed phase. What's the volume fraction? How do you want to model the release from the droplets? If you know something about the droplet size, you can put that in. Okay. And then finally, at the bottom here, you can see that we have what we call TD reservoir patch. Okay. So essentially, this is meant to model the case where you have a transdermal patch where the release from the patch is slower than absorption into the skin. So essentially what happens is as soon as your drug is released from the patch, it's going to be immediately absorbed into the skin. In these cases, this is sort of going to end up being sort of an empirical model. So you as the user need to provide a release rate. Okay. And if you're familiar with GastroPlus, this is going to be modeled in the same way as the controlled release dosage forms. So you can either specify this as sort of tabulated, you know how much is released at different points in time, or you can use a Weibull function to have sort of a smooth curve of the release. Okay. So getting a little more into the nitty gritty of how some of these processes are modeled. So you can, again, one of the important processes is going to be the potential evaporation of the vehicle. The way that we model this is essentially you're going to have the top layer of the vehicle, you're going to have the bulk air phase, and then between those you're going to have this air phase boundary layer with a concentration that you can calculate. Okay. So essentially the solvent evaporation rate is going to be roughly equal to this concentration multiplied by the application surface area, but then it's also going to be multiplied by this K-evap term, which is going to be the rate of determining the rate constant of the evaporation. Okay. So of course the next question is, okay, well, how do I get this K-evap term to let me know my evaporation rate? Okay. So when we looked into the literature, we found several different equations meant to estimate this K-evap term. As you can see here, generally these are going to be based on things like what's the diffusivity of your vehicle in the air, what's the kinematic viscosity, what's the ambient air velocity, what's sort of the characteristic length. This is basically going to be related to the surface area. Okay, and also things like the molecular weight of the solvent can also be playing a role. Okay, so when we were originally developing the module, we had all of these. We didn't know which one was best, so we said, okay, let's just provide all of them to the user. Since then, we were able to do a collaboration with the Cosmetics Europe Consortium, which is particularly looking at, obviously, compounds that are of interest to cosmetics. And in that case, we were able to look a little bit more in detail, and it seems like the Nielsen model may be the most accurate one. Okay, but at the same time, we still provide all of these to you. Okay. However, you aren't forced to use these. If you already know the solvent evaporation rate, or if you want to explore the effects of the potential solvent evaporation rate, you can also just put in a user-defined evaporation rate, and you can also choose which unit you want to put that in. So, if you're working with your own formulation, your own vehicle, obviously, measuring the evaporation is pretty easy. You just put it down and see how long it takes to evaporate. Okay, so so you can just put a value in here, and not try to bother with all of this estimation. Okay. And this is just showing some of the work from the Nielsen paper, where they were also looking at some of the previous models. So, unsurprisingly, in their paper, their model performed the best. And as I said, as far as we can tell from limited data, that this one is our default, and it seems to perform best. This is showing the vehicle evaporation setup in the TCAT module. When we get to our example, I'll show you how to reach the screen. So essentially, there's going to be a lot of different parameters that are going to go into this, solvent vapor pressure, solvent air diffusivity, and so on. And then there'll be this drop-down menu where you can choose which type of model you want to use, or if you just want to put in your own evaporation rate. The program will also show you down here, based on the rate that you put in, roughly what the evaporation time will be. Okay. Now you might say, okay, who cares about this? Why is this important? Is this going to matter? The thing is, this matters sometimes. What we've seen as we've looked at a lot of different APIs and formulations, in some cases, this vehicle evaporation doesn't really make a difference to the absorption. You turn it on, you turn it off, there's no difference. Okay. In other cases, it makes a difference whether there's evaporation or not, but the specific rate doesn't necessarily make a difference. So, if you turn evaporation on, you see a difference versus, not including vehicle evaporation, but changing the rate, it's not very sensitive to the actual rate. Okay. But you do finally get the cases like the one that you see here, where when you include evaporation, vehicle evaporation, you do see differences, and it is sensitive to the rate. Okay. So just kind of to go through this plot, here you're looking at the concentrations of a compound in the vehicle, stratum corneum, viable epidermis, and dermis. And here you can compare no evaporation to having a solvent evaporation rate of 0.02% per second. So what you'll see here is the result of this is that you're going to have an increase in the concentration in the vehicle, right? Because your vehicle is evaporating, so the remaining API is going to be concentrated. And that increase in the concentration is going to increase the concentration gradient. So this is going to drive increases in the concentration in the deeper skin layers as well. Okay. You can see that's also going to be significant, again, what your evaporation rate is, because that's going to affect exactly the point at which evaporation is going to end. Okay. In this case, now we've increased our evaporation rate, and you can see that that's going to change the shape of all of these curves. And again, if you have a much higher evaporation rate, then that's going to also cause a change. Okay. So, this is something that you should think about. Is this going to be significant and important given my API and given my vehicle? Another thing that we've included in the TCAT module, and this is something that's new in GastroPlus version 9.7, is including compound evaporation. So in our previous slides, we've been talking about the vehicle itself evaporating, but the API that's within that vehicle can actually be evaporating itself. Okay, so again, as part of our collaboration with the Cosmetics Europe Consortium, we had enough data that we could start to build out models of this compound evaporation. Okay, this is turned off by default, but you can check the box here to turn it on. Okay. One thing that we were able to see from their very extensive and very good data was that usually what will happen in these cases is you'll only have a certain percentage of the compound that evaporates, and then the rest of it is going to remain in the formulation. Okay. So what we have here is going to be the compound residual amount. So if this is 15, then that means that 15% of the compound is not going to evaporate, whereas 85% will evaporate. This value can be estimated from what's called Henry's law constant, which is a measure of volatility. And this is also actually a prediction that we can have for compounds based on the from ADMET predictor based on the chemical structure of the compound. Okay, so if you're importing your own compounds and you want to see whether or not they're likely to be volatile, you can import them, and then once you go to this box, you can delete and double click, and then the program will estimate and tell you, how much residual amount do we think that there will be. If it comes out at 99%, obviously we don't think it'll be volatile, but if it comes out lower, then you know that this compound may be volatile and may be evaporating. The other part here would be, okay, well, if my compound is evaporating, then what's the rate of evaporation of the compound? And unfortunately, in these cases, we did not have enough specific time course data to be able to give good estimates for this. I can say it seems to be on the high side, like maybe something more like 2% per second or 7% per second. But in this case, unfortunately, we don't have enough data right now to provide estimates for this. So you would have to specify a particular compound evaporation rate. And you would also be able to see down here what's the predicted evaporation time. So that's going to, that should at least, give you an idea of, whether it looks right.
And this is a good spot. Thank you, Jessica.
Yeah.
Quick question for everyone as we're going through the slides. What's your current interest in using the TCAT models? Choose all that apply, support formulation development, inform your QSP or PK/PD models. We'll give you a couple of seconds to answer, and this will also help Jessica as she goes through the remaining slides and gets into the case examples on just what your use would be for this model. So just a few more seconds here to collect the responses, and then we'll get back to our program. All right, so it looks like, Jessica, we've got a lot of people interested in using the model to support formulation development. Go ahead and take it away.
Sure. Okay. So in that case, that means it's good that I'm going a lot into the different vehicle aspects. Okay. So, so if you're modeling emulsion dosage forms, again, these are going to be cases where you're going to have dispersed phase droplets that are going to be within some continuous phase. So one of the things that we need to figure out here is going to be, well, what's going to be the relationship between the concentration in the dispersed phase and the concentration in the continuous phase, because you can have transport between these. Okay. So we have two models for this, equilibrium model and diffusional model. The equilibrium model is going to assume that there's going to be a constant ratio between the concentration in the dispersed phase and the concentration in the continuous phase. Okay. This value is going to, the default value for this is going to be based on log P, okay, because kind of the P in log P or the D in log D is actually going to be this type of ratio between octanol and water. So if you have oil droplets that are your dispersed phase and water in your continuous phase, the log P is going to be a good starting point. Okay. However, if you do have something more complex, maybe you have water and oil, or maybe you have some oil that's significantly different than octanol, then you would want to choose a different value here that again is going to be based on on the difference between the concentrations in dispersed and continuous phase for your specific vehicle. Okay. And then this value is kind of going to go into this equation that's going to be determining what the release rate is. For the diffusional model, the idea is that in this case, your droplets are going to be surrounded by a thin membrane or surfactant layer. So drug has to diffuse out through this surfactant layer to get from the dispersed phase into the continuous phase. Okay. So in these cases, you would need 2 additional parameters. One would be what's the diffusivity of this membrane or surfactant layer, and the other question would be what would be the thickness of this layer. Okay. A final thing to mention here, a lot of people ask about this. You can have, of course, the free-floating droplets, where there's only going to be transport between the dispersed and continuous phases. But you can also have these droplets that are going to be adsorbed to the skin. So they're stuck to the skin, and you can have compound going directly from the droplets into the skin, in addition to going from the continuous phase into the skin. So you can start actually have some pretty complex modeling. Depending on that adsorption area and the properties of your vehicle. Okay. So this is showing the emulsion setup in the TCAT module. Another thing that you want to set up here, obviously, would be what volume fraction of your vehicle is going to be dispersed phase. Okay. And again, this is where that dispersed phase partition coefficient is going to be. Okay. And then you can choose down here which release model you want to use. Okay. So those are all the major aspects that we're going to think about when we're looking at the vehicle. But what about when you start to get into the skin? Okay. One thing you have to think about immediately is we can't really model these skin layers or the vehicle really as being well-mixed compartments. Okay. If we said that these were well-mixed compartments, then basically that would mean that, for example, the concentration over here in the stratum corneum near the vehicle would be the same as the concentration over here near the viable epidermis. And the only difference between the concentrations and the different layers would just be according to their different partition coefficients. Okay. But we know that in reality, when you're applying a topical dose, we're not in this kind of very stable, steady situation. Instead, we know that compound is going to be coming from the vehicle in diffusing down through stratum corneum, diffusing down through viable epidermis, diffusing down through dermis. So we can't say that we have the same concentration here and here, right? Really, we expect the concentration to be higher in the part of the stratum corneum that's near the vehicle, and then lower over where it's going to be near the viable epidermis because of the concentration gradient. Okay. So the way that we deal with this is that we divide each of these skin layers as well as the vehicle into what we call sublayers. Okay, so by default, stratum corneum is divided into 10 different layers, and so now we can have a different concentration in each of these different sublayers so that we can capture this internal concentration gradient within the skin layers. Okay. When we were first developing the module, we thought that this was going to be, really, really important. In practice, we've set default values to have 10 sublayers in stratum corneum, 5 in viable epidermis, 5 in dermis, and that works pretty well. Okay. But if you've been looking at the tabs here, maybe you have GastroPlus, and you said, okay, well, what is the sublayer tab here? That's what that's going to be. Is again, we divide each of the layers into sublayers in order to capture these concentration gradients. We also have some very extensive sets of equations to estimate the partitioning and diffusivity in each layer. So obviously each skin layer is going to have its own permeability, and you can divide permeability into diffusivity multiplied by partition coefficient divided by the thickness of the layer. Okay, so we know the thickness based on the physiology, but this diffusivity and partition coefficient are going to be specific to different APIs. Okay. Broadly speaking, diffusivity is going to be mainly affecting the diffusion within each layer, and the partition coefficient is going to be affecting the transport between two different skin layers with different properties. Okay. So if you look in GastroPlus, you'll see that we have several different models to estimate these. For the stratum corneum, we have a Wayne-Casting-Niche model, a Potts-Guy model, and also a Robinson model, which was an internal model from P&G. And then for the viable epidermis, we're going to have Kretzos model, Bunja-Cleek model, and then the Robinson model was in 2 parts. So we have a Robinson model for stratum corneum and a Robinson model for viable epidermis and dermis. Okay. Usually the assumption that we make is that the viable epidermis and dermis are going to have very similar permeability. So we have a checkbox to automatically assign whatever values you're using for viable epidermis to the dermis. I believe in terms of the models, the Kretzos model was originally developed for dermis. Bunja-Cleek and Robinson were originally developed for viable epidermis. But of course, you can also look up the original papers to see all the details. Similar to the vehicle evaporation models, when we were first developing this, we weren't entirely sure which one was best, so we just put all of them in. Since then, we've done, again, some extensive modeling with the Cosmetics Europe Consortium, and we think that the defaults for these are going to be the best ones. So using the Wayne-Casting-Niche model for the stratum corneum and the Kretzos model for viable epidermis and dermis. Having said that, though, once you get down into individual compounds, there are individual compounds where, for example, the Potts-Guy model might be better or the Bunja-Cleek model might be better. We also have an estimation for the diffusivity and partitioning in the sebum. And if you look in that case, you'll see that we have predicted equations that were derived from 2 papers by Valavetti et al. Okay. Since then, there's been more data published, so we were able to build what we think is a better correlation. So it's not in the current released version, but we are developing more detailed equations here based on these 2 papers by Yang and Lian. So something to look forward to. We don't have any default predictions for diffusivity and partitioning into hair. Our default assumption is that compounds are not going to go into the hair. Okay, but obviously, if you're modeling, for example, a hair dye or something like that, then you would want to try to figure out some values. Okay, and I would mention also for all of these, you do also have the option to put in user-defined values. So if you have measured values, or if you want to, explore the sensitivity, you can switch any of these to user-defined and put your own values in. So this slide is just showing some of the predictions, and again, comparing the predicted results with the predicted results with the actual experimental results for several of these different models. These 2 at the top are going to be in stratum corneum, the Wayne-Casting-Niche model. This is going to be the Potts-Guy model that we also include. Okay. And then this, I believe, is showing some of the results for the Kretzos model. So if you open up GastroPlus, and again, I'll show you guys where this is, then you'll see over on the side here what's the specific, the place where you can choose which type of model you want to use. And again, once you're in the viable epidermis or the dermis, then you have the possibility to specify some local metabolism. So once you get down to the dermis, now we're getting into the perfused tissue. It's possible for drug to diffuse into the capillaries and enter the systemic circulation. Okay. If you're modeling transdermal formulation, you want this to happen. If you're modeling a topical formulation, you probably don't want it to happen. But either way, you want to have this system accurately described. Okay. We're going to model the systemic absorption as a first order process. So you'll have systemic rate absorption constant, and then that's just going to be multiplied by the concentration gradient between the dermis and the systemic circulation. Again, this can go both ways. If you have more compound in the systemic circulation than you do in the dermis, you can have compound diffusing back. So we don't make any assumption about which way it's going. Okay. So this case, you can directly put in this case value. But we were also able to include a model predicting this case value, which is going to be based on the properties of the capillaries in the dermis and the rate of the blood flow through the dermis. And that's going to be the Ibrahim model. You can see the reference down here. and that's going to be the default and going to be predicting the case, that case cis. Okay. So just kind of to summarize things, what type of inputs do I need, if I'm going to use this module for real? Okay. First thing is going to be the physiology. Okay, you want to know obviously which species you're looking at, but it's also very helpful if you do know something about which region you're interested in. Okay. You're also going to need to input some administration parameters and formulation parameters, right? We can't predict which dose you're using and so on. You have to provide that type of information. And you also need to include information about the formulation parameters. I talked about a lot of these, but another very significant one that's going to be very important is going to be what is the solubility of your drug in your formulation. Okay, if your compound is, if your formulation is aqueous, then you can just use the aqueous solubility here. But if it's significantly non-aqueous, then you're going to have to give the information about the solubility. Okay. And this is also going to be potentially affecting the partition coefficient for the vehicle if you have a significantly non-aqueous vehicle. And of course, finally, once you get into the skin, you're going to want to know something about the diffusivity and the partitioning. But again, we do have a number of published equations to estimate the partitioning between layers and the drug diffusivity in each layer. There is one important thing here, however. All of these equations that I've mentioned about the tissue partitioning and the diffusivity and also the systemic rate constant, these were all developed based on human skin. Okay, so if you're modeling a preclinical species, these equations may not be accurate and you may need to gather additional data. Speaking very generally, the preclinical species are going to have higher skin permeability than human skin. But unfortunately, we don't have enough data yet to be able to quantitatively predict, mini pig skin permeability, as opposed to human. Okay, so this is kind of a limitation right now. These equations work very well for human skin, but they may not work as well if you're modeling a different species. So you may remember from a while back, I was talking about how we have this model of the in vitro skin. This was another part of the model that we developed through our collaboration with the Cosmetics Europe Consortium. And this was just showing some of the results that we got for that. Essentially, what we did was we had kind of 25 compounds, and we did kind of blind modeling to predict under the in vitro situation how well they would permeate through the abdominal skin and reach the receptor fluid. Okay, and these were the results that we got from that. Okay, so as you can see, overall we were getting very good alignment and comparison to the observed percentage in receptor fluid versus the predicted percentage. Okay. One interesting thing about this was, in this case, most of the compounds were administered in phosphate buffered saline, but there were also 4 compounds that were administered in ethanol. Okay, and in order to correctly model the compounds that were in ethanol, we actually had to adjust the vehicle partition coefficient. So again, if your formulation is significantly non-aqueous, then you would probably want to be thinking about the vehicle solubility and also the vehicle partition coefficient in order to get good predictions for those, or good models for those compounds. So if you want to use the in vitro dermal physiology, essentially this is going to be how it's set up. So the idea here is that you would have some dermatome abdominal skin, and it's going to be going from the donor compartment at the top and the receiver compartment at the bottom. Okay. So it's kind of limited right now. And that's the reason why, as part of our grant that we're working on with the FDA, we are going to develop this into a full-blown in vitro dermal modeling of skin samples in our Membrane Plus software. So this is something that we're working on right now. There's going to be a lot more flexibility in terms of the number of skin layers, more flexibility in terms of modeling of the vehicle, and also more flexibility in terms of modeling the diffusion cells. So something to look forward to in the future. Okay. So at this point, I'll see if I can get through this in 10 minutes. So we have 5 minutes for questions. But I want to give an example. And the example is going to be looking at a diclofenac topical solution. Okay. So what we had in this case was there were two topical solutions of diclofenac with concentrations of 1.5% and 2%. Okay. We didn't have a lot of information about the formulation, and unfortunately this is kind of a perennial issue when we're trying to model these formulations, is oftentimes we don't have very much detail about the composition of the formulation. But in this case we did know that it was 45.5% DMSO. Okay. In this case the solution was applied to both knees in the forms of diclofenac salt. And we know that 19.8 milligrams of diclofenac salt was applied to each knee, I think in the case of the 1.5% solution. Okay. So after this data, then we had, you can see here that we had the mean plasma diclofenac concentrations for 24 hours after this administration. Okay. So given this type of information, well, how can we model a topical solution of diclofenac? So hopefully you all can see my screen here. So this is kind of setting up the diclofenac database. And if I look at the drop-down menu here, I can see that I have 5 records. Okay. The first record here is just an import of the structure of diclofenac with all the predicted properties. Okay. And the second record here is including some of the experimental values. So for example, we had we changed the solubility here based on experimental data and so on. Okay. The last 3 records here, you can see that we have a record based on the IV bolus and also records based on 2 different IR tablets. Okay. If you're modeling a transdermal or topical formulation, it's a very good idea to, as a first step, have a good systemic model. Okay, so in this case, we had an IV injection of diclofenac, and we were able to build a compartmental PK model based on this. When you're using the TCAT module, you can use this in conjunction with compartmental models and PBPK models. Either one works. Okay. But if your compound is going into the systemic circulation, you want to have some confidence, obviously, that the distribution and clearance from the systemic circulation is going to be accurate. So I would always suggest that you should start off by building a good systemic model. Okay.
Jessica, could you expand your gastro view?
Sure. Is that helpful?
That's helpful. Thank you.
Okay. No problem. Okay. In this case, for additional confidence, again, we also were able to model the oral tablet doses of diclofenac. I would say for the TCAT module, this isn't going to be as important, and the reason for that is because we don't have gut absorption. So having a good model of gut absorption, it's nice, but it's not really as necessary. But it does give us greater confidence, that our systemic model is good. So, so once you've done your more basic modeling, you have a good systemic model that you're happy with. The next thing that I'm going to do here is go to database, copy drug record. Okay, and now I'm going to create my first TCAT record. Okay. So this is going to be, at first I want to model my diclofenac dermal 1.5% solution. And obviously the first thing that I'm going to do here is going to be to start change to a TD dosage form and start to put in my information. Okay. This is a solution, so I'm going to want to go with TD liquid solution here. Okay. In this case, if we convert the dose of the diclofenac salt into kind of the free version, this is going to be 35.81 milligrams. Okay. This was applied every 6 hours, and if you have regular repeat dosing, you can do that with the TCAT module. So my initial dose is 35.81, all my subsequent doses will be the same, and it's applied every 6 hours. Okay. If I calculate out my dose volume, in this case, it was going to be 2.57 milliliters. And again, this was all based on the information from the NDA. Now, if I want to go and look at the TCAT module or make any changes to it, I can come up here to modules, additional dosage routes, and number 3, transdermal. Okay. Since I already chose my TD dosage form, you can see this is definitely going to be on. I can't turn it off because having it on is the only thing. And if I click that on button, then I'm able to, I'm not sure if maximizing this really helps very much, but I'm able to open up my TCAT module here. Okay. So if you remember, this was applied to the knee. So if I'm choosing, oh, that's interesting, a physiology here, I'm going to want to choose the human leg. Okay. And then I need to also add some additional vehicle properties, right? I put in my dose and my dose volume, but I don't have an application time or application surface area. So you can see that my dose and my dose volume automatically were populated here. But the default surface area is 1 centimeter squared, and this was applied to both knees, so it's definitely going to be more than 1 centimeter squared. We did a calculation of what I don't think the specific area was reported in the study, but we did a basic calculation based on kind of the knee being a cylinder. And if we do that for both knees, it's going to come out to about 725 centimeters squared as our surface area. Okay. If you leave the application time at 0, that's going to mean that the dose is going to be on the skin for the full time. Okay. But if it were only applied for 1 or 2 hours before being wiped off, then I would go in and change that value. So again, we know that our formulation was 45.5% DMSO. There's a big question here, you know, when we have these parameters like solvent molecular weight, what value should we put in if we have a complex formulation with many different components? This is something that we're also not entirely sure about. But usually what we'll do is, at least right now, is just to put an average in. So in this case, they put in like 45.5 grams per mole as an average. And we also want to change the solubility of the API in the solvent. I think in this case, it ended up being 15 milligrams per milliliter. Okay. You can also look at the other tabs here. Okay. So for everything else, let's just start off with the default values. Okay, so I'll just click Save here. And then I'll go to the Simulation tab and run a simulation and see how good it is. Now, even before we get to the Graph tab, I can just look down here and already start to see some problems. We had with our observed data for this, we had a Cmax of about 13 nanograms per milliliter, but currently the calculated value is 0.2. So, and if you look at the Graph tab, this is looking at the plasma concentration. Okay, something clearly went wrong here, right? Okay. So again, you know, our default permeability equations seem to broadly work well for a wide variety of compounds, but we do still regularly run into compounds like diclofenac where just using the defaults isn't sufficient. Okay. I want to keep some time for questions, so I won't go all the way through this the way that I usually would. Essentially, the first thing that you'll want to do in these cases is start to look at some of the different permeability equations. Look at what they're predicting for diffusivity, partition coefficient, and overall permeability. And in particular, look and see whether maybe one of them is an outlier from the other two, because that might be explaining it. Okay. In this case, if you compare Kretzos to Bunge-Cleek, for example, you'll see that there's going to be a big difference in the partition coefficient, big difference in permeability. Okay. And in fact, if I switch this over to Bunge-Cleek, now like magic, since this is a workshop example, you can see that now we're getting much better results in this case. Okay, so so this is the type of thing that you're going to want to think about. I won't go through the last part of this. It would essentially just be copying this record and showing that this model built based on the 1.5 solution also works very well for the 2% solution. Okay. But this is the type of thing that you're going to want to think about when you're developing these models. And I would mention also that it's always going to be a good idea to start to calibrate them with kind of an initial set of data, where topical or transdermal data where you have some information. Okay. So I just have a few other slides just showing a few more types of examples. In this case, we had a Bopindolol transdermal patch. And again, this would be the case where the user supplies a release rate. Okay. And essentially what we did in this case was we fit that release rate based on one record, and we were able to model the effect of applying it for different periods of time or applying different doses. Okay. I also have a few slides. These are ones that we did in collaboration with GSK, looking at modeling of different Clindamycin formulations and different tazarotene formulations. Okay. So here's just a big list of some of the citations for this. And thank you very much. And I think I managed to leave 5 minutes for questions.